Afternoon. I hope everybody survived lunch. My name is David Rolfe. I'm here with my colleague Tom Howcroft. From VoltDB, we're based in Bedford, Massachusetts, and we make a high-performance transaction processing database. This is probably not like a lot of the presentations here over this couple of days, in that we're not overly technical. It's more about the practicalities of working with very large quantities of data and very large things. It's based partly on the stuff we deal with at Volt every day, and partly on my own personal experiences. Before I worked for Volt, I worked for an Irish software company which did a lot of work with US telephone companies, and at one point we were dealing with 24 billion records a day. When you're dealing with billions of something, small problems, unlikely events start to happen all the time, and there's a whole series of things you hit as you scale that aren't related to a specific technology, aren't traditional sort of blog material, and are the kind of lessons which may sound obvious, but until you've experienced them for yourself, you don't know it. So I'm going to start now. At the end, I'll be delighted to take questions or do whatever, and we should start, I guess. First, I'm going to cover scaling at the architectural level, which means, architecture, basically. Even though we have more and more CPU power available, even though we have vastly more resources available to us than we did the last few years, you still have a requirement to have more than one computer ultimately. Simply high availability requires you have to have a second copy of it. The traditional high availability model, which is pursued through the 90s and early noughties, would be, well, you'd have another backup server, a standby server. And the problem with that is that you go through all the pain of making your system run on more than one computer, and then you have to have 100% spare capacity, because so the other surviving server has to be able to pick up the load. As you increase the number of servers, the actual additional required spare capacity starts to go down. So don't just assume when you're looking at making anything highly available that having two big servers is the answer. Which gets us into, well, how do we decide how many servers we need? Something is going to be a driving factor here. And the problem is you may not know this until your application is up and running. At a minimum, high availability dictates you've got more than one of everything. It could be RAM bound, it could be CPU bound, it could be network bound. At Volt, we have hit network probably more often than we've hit other things. Then RAM, CPU is rare for us. And don't make the mistake a lot of people make, which is they go into a room with a whiteboard, a long way from any of the business people who have to sell it, or any of the customers who have to deploy it, say, this is what it's going to be. It's going to be exactly this. It's going to run on this color server, pointing south, which the Feng Shui department says. And the reality is you may not be able to dictate anything, for two reasons. One, in Amazon, for example, you may find that in order to get enough network capacity, you have to use a certain size server. So you may be running at 15% CPU, clocking up a larger build than you planned, but that's what you need to get the network access, network bandwidth you need. Because anything which involves more than one computer now has a lot of network traffic going on behind the scenes, which isn't necessarily directly related to what you're doing as a customer. The other thing is someone else's cloud. A lot of organizations want private clouds, and the private clouds, as my bad joke goes, it's a bit like air travel. They advertise business class, and you get economy. So my average private cloud server for a US telco, for example, I think was 192 gigabytes of RAM and 8 cores. That is not what we planned at the whiteboard level. That has implications. So how many servers you need is not something you can dictate in advance. And as you get bigger, a different phenomenon kicks in, which is that as I have more and more servers, I have to get more and more paranoid about the fact that something is going to go wrong. Google have done a whole series of, there's quite a lot of Google, everybody's coming in now, okay. Google have done quite a lot of stuff which they've released to the public about running big data centers. And of course, there's a bit of Google chest thumping going on there, but there's also some real information, such as that once you reach a certain size, a portion of your service will be like a military academy. At any one moment in time, some of it will be passing out and stopping working. you'll be in a world where there's always something broken somewhere. Which means if I've only decided to have one spare copy of the data, either by architectural design, the risk of suddenly having no copies of that data goes up. So we have a large telecoms customer with a heavy presence in Finland who were deploying 9-node clusters, 8 of which were active, basically pairs, and the 9th one was what we would call a wallflower. Its job is to continually try to join clusters. So when something went down, it would try and join and take over. Now, we worked it out that the probability of that, of having 2 simultaneous independent failures of telco-grade hardware in a data center at the same time was roughly 1 in 3.5 million per deployment, which is, interesting enough, the same chance you have of being trampled to death by donkeys in the Republic of Ireland any given year. But the more nodes you get, the more likely it is that you could have 2 or more awfully inconvenient failures happening at the same time. So once you reach a certain size, you can no longer have 1 spare copy, you now need 2. So what you're seeing is reverse economies of scale kicking in here. As you get bigger, once you get to a certain level, you now need more stuff than you thought. And then the other thing is, with these systems, it depends on your line of business you're in. But in some businesses are very peaky, telecoms especially. What do you do about the peak? Do you size for the 1 in a year annual event? Such as in the Middle East, there's I think some festival where everybody sends each other text messages, which means everything has to be sized for that 1 20-minute period. Or do you deliberately generate a busy signal and say, we're giving you a degraded service, i.e. none, but at least we're telling you we're not giving you a service, we're not just hanging up. Because that could have significant economic impacts. And that's also a business decision, because it may be part of your value that you're always up. But what does always mean? This is where it gets interesting. When I started out, active, by which I mean the same database in 2 data centers with people updating both copies at the same time and everybody being happy. That was science fiction a few years ago. And it's now getting very common. And the motivation is fundamentally survivability. It's the proverbial asteroid hitting the data center. And the other thing which you're seeing, which is going to become really common with IoT and 5G, is that the speed of light is 186 miles per millisecond. And as latencies go down, you now need to be much closer to the data than you used to be. Because at 168 miles per millisecond, that means Britain is now, about 7 milliseconds round trip. So if you want to get things done really quickly, you might need multiple data centers even within the United Kingdom. For countries like the US, which are huge, you are guaranteed to need multiple data centers. And the other motivation is and always has been ego. Don't underestimate the desire of people in corner offices to want these systems without necessarily understanding how they work. And the key thing for any kind of active deployment is, how does it work with the rest of the system? Because there's no point you making one individual system active and be able to survive all this stuff if none of the other infrastructure can, or if it does it totally differently. Don't assume that active helps you scale. You still have to send everything which happens at site A to site B and site C. In Volt, we have active as a basic product functionality now. It's still a 10 to 15% overhead of applying changes from other sites. So if, for example, I add a 3rd site which does nothing except exist, that's now another 10 to 15% overhead on everybody else. And then it starts to get ugly. At some point, you have to partition the data. You can't fit it all onto one machine. For low latency environments with lots of writes, you're going to have to partition it. Now, this is an in-memory database summit, so I'm assuming I won't have to spend days explaining that to people. And you have to partition it somehow, and you have to figure out what you partition it on. In a lot of businesses, it's blindingly obvious. In some, it's not. In some, it's really awkward. We have a concept of materialized views, which allows you to go across partitions, in that we allow to maintain summaries which are completely independent of the partitioning keys, which help for keeping running totals of things. We can talk about that later if you want. Pet peeve of mine, people going on about eventual consistency. If you've got multiple copies of something, if I'm partitioning data and I've got multiple copies in 2 different places, the problem with eventual consistency is if anybody reads it before it becomes consistent, It's like one of those 1980s time travel movies where somebody goes back in time and changes something. The information, the moment somebody has read your data before it becomes consistent, the information has leaked. It has left the building. It is now in the outside world. It's like the butterfly effect. In a world where we're trying to affect things at very low latencies and influence the moment, things that are happening right now, eventual consistency means I could read something a millisecond before it changes to the correct value. I could go off and take a series of decisions of cascading awfulness based on that. There's broader implications at the architectural level. We're no longer talking about something which is cute and furry and sits on your laptop. You're talking about something which involves as many moving parts, is spread over many places, has many different technical specialities involved. You could have network people, storage people, different people, visits to the application be done by different people. It's not trivial anymore, which means that the development and testing costs start to go up geometrically. If people can't have their own copy and you've a limited number of test environments, that starts to act as a massive bottleneck. Because you can't have everybody running around doing their own thing, because the nasty aspects of the system that you need to watch only become apparent at very high levels of throughput and scale. You may be looking at effects which you may be the first people in history to observe them because of the volumes they're working at. So, and this means that you may only be able to afford one proper test environment. So how many developers do we have? What does that mean? How many iterations can I be working on at once? And this means that if your development test environments are significantly smaller, you could have issues. And the other thing people tend to leave out is, okay, I've got my system that's 100 terabytes and I'm doing a zillion transactions a second. What exactly do I connect it to for test purposes? Because one of my favorite concepts is the idea of Kung Fu villain syndrome in testing, which is where all your test data shows up like the villains in 1970s Kung Fu movies, 2 at a time, ready to be dealt with appropriately. Real world traffic is nasty, it's irrational, it's unreasonable, it surges when you least expect it. If you've got cheap, crappy emulations of the environment you're in, of course you'll scale. It'll work wonderfully. And then you go live and you're all there at 4 in the morning wondering what the hell happened. At this point, I'm going to focus on the write-intensive workloads because that is very much Vault's thing. You can't scale writes the way you scale reads. Traditionally, you scale by adding more of what you're not using, what you're running out of. So commodity hardware is really good for scaling reads because you're basically having copies of it and you can add more CPU and RAM and stuff and you get away with it. Some writes scale well. If they're disconnected from everything else in the universe, you just need a record of it, you just blast it onto disk and you go. But if the writes have some kind of element of transactionality, it's too early in the day to be saying that, you can't just do 2 updates. You can't do it in 2 places at once. You have to actually start thinking this through. And all of a sudden, you're in a world where the bottleneck is no longer the physical resource. It's no longer something I can buy more of or rent stuff on Amazon. The bottleneck is now the data itself. And this is something we haven't necessarily seen before. We went through an era for about 5 to 10 years when every 6 months, hardware got cheaper and more available. Every 6 months, we could add more and more stuff. We got networking figured out. We've distributed systems largely figured out. But what happens if there's only one account and I need to decrement a counter in it, and there can only be one by definition, and I have to, and because I'm using something of value, how do I scale that? So this is so if you looked at traditional database write strategies, and how do you do this? Originally, they had row-level locking. And row-level locking is where you show up, you're the only person who touches the resource, you update the resource, you come back a few seconds later, possibly minutes, and finish your transaction. Until that happens, nobody else can do anything. So if we're keeping track of how many orange juices we have left, nobody can buy orange juice till I leave the store. Then we've got eventual consistency, which is where you take the orange juice, you go out to your car, and while you're putting it into the car, it vanishes and goes to somebody else's car. Now, don't think I'm completely against eventual consistency, but in the space Vault tends to work with, where we're dealing with finite resources that generally count downwards until something bad happens for somebody, it's not good for us. There's optimistic updates has come out as an alternative, which is where you buy the orange juice and then they tell you to bring it back. And Volt is more like probably vending machines where we make you buy it at the point of sale. And to give you, this is where I'll go a little bit into how Volt works. What we said was that traditionally, in a database, the idea was you'd have lots of people coming in and they'd be manipulating data in RAM, and in a shared database, it would all get written to a shared SAN. This is how products like Oracle RAC and IBM's transaction, whatever it is called, work. The problem is that at the simplistic level, when I've only got one CPU, keeping track of what all the users are doing is my job. I just have to make sure they don't see each other. As I add CPU cores, I now have to worry about what the other CPUs are doing as well, because I've got people helping me. And if I don't have any clear rules for which CPU or core is working on which data, you have lots of scenarios that you have to allow for where people are different CPU cores could at the same moment in time be manipulating data you're trying to manipulate. And all this stuff about the data being the bottleneck suddenly becomes highly relevant. So at Volt, what we said was, we've got a finite number of cores on our box. I remember being in a room with Tom Kite about a decade ago, and he was pointing out that at that time we had 8,000 sessions open. You only got 8 cores on the box, so you can only do 8 things at once. It's a fairly interesting point. You can't really argue with it. So what we said at Volt was we're going to partition the workload by the CPU core instead of the server. So we look at the incoming transactions. We do a hashing algorithm to figure out which core they belong to, and they go into a neat, orderly queue. Now, the key difference between Volt and a traditional relational database is that the transaction has to begin, start, and end in the trip to the database. In the 1980s, 90s, this would be heretical. No, you can't do that. Most of the people in the room, this room, are going to be working with systems where there is no human in the loop. You're speaking with another computer system. You're speaking with an internet standard. It just wants an answer, and it wants it quickly. There will be nobody there looking over their keyboard, waiting to press F10. This isn't 1988. So what happens is we say the transaction, you send us a business problem. We execute SQL on the server side using stored procedures, which are terribly unfashionable, but work. And then we send the results back. Now the key point for us is that when I'm buying item 1 there and buying item 2 there, it's guaranteed to go to that particular CPU core. And that core, because it's a single core, can only do one thing, so we have a single-threaded process which does one transaction at a time. And again, this seems completely counterintuitive, but if I've got 8 cores, the most efficient way to use them is to have a thread per core, which is doing the work. Because the transactions can't start and finish independently of reaching the database, when I finish the first transaction, I start the next one, they never see each other's work in progress. Doesn't happen. So that allows us to scale quite dramatically, where we've done millions of transactions in benchmarks. We have people doing hundreds of thousands of transactions in the real world, and we're about 9 to 15 times more efficient than a traditional RDBMS based on that. So, on to the fun stuff, things which happen in the real world. There are 6 things I've figured out over time which people need to know, and they're not conventional, marketing speak things. There's a guy called Nicholas Taleb who did a book called The Black Swan, and he writes about the concept of Ludic fallacy, which is if you turn something into a model and start using the model to predict reality, sooner or later something which cannot happen in the model will happen, and then you're screwed. So if I'm going to do things like I could model the real estate market and then fail to allow for earthquakes. He came up with the concept of a black swan event, which is something which everybody afterwards said was blindingly obvious, but nobody predicted beforehand. The 2008 crash was blindingly obvious after the fact. Everybody was telling everybody else, but nobody saw it. And why is this relevant to us? We rely in our profession on modeling reality, and our model has to simplify reality. And in the process, we could be leaving something out, something quite nasty. As you scale, the possibility that there's a scenario out there you haven't thought about starts to become bigger, more likely. Here's a real-world example of Ludic fallacy in action. This happened earlier this year. There were a whole series of late last year, there were nasty fires in Southern California. So Google started directing drivers to the roads where the fires were because they were empty. And there you go. The next, it's actually happened to me. Your data will always be slightly wrong. As you scale, real-world data streams always have errors. There's always something wrong. It might be 1 in a million records, but if you're doing billions of records a day, this could add up, and it could have nasty implications. So a basic fact of life is a car can only have one chassis number ever. They don't change the chassis number on a car. Well, this particular car was moved from California to Ireland, and in the process, they changed the chassis number. Now, we're all thinking, oh, this is harmless. It's not harmless if you're moving stuff around. It now means that even though they corrected it, and I've got 2 sets of title paperwork at home, there is now a ghost car wandering around Dublin. It will exist forever. 150 years from now, it'll be the oldest car on the roads. And it just shows your data, it doesn't matter. Even if it's machine generated, there will be something wrong somewhere as you scale. Once you get the 1 in a billion chance at 24 billion transactions a day is happening every hour, fantastically unlikely things will start to happen to you. And again, it's also an eventual consistency argument there as well. And then you get into the reality of trying to predict, I'm trying to join stuff in the real world. So let's just take your classic example. I want an application to predict flight delays. And there are people who've taken real world data sets and they've done this, and there's a data set of US flights, and they take it and they say, look, I can produce an engine which will predict with a certain degree of reliability whether a flight on a given day is going to be late. And they use historical information, but I need to do this in real time. And so you have the schedule, everybody has that. You have aviation weather, which we now need to update every few hours because that influences what can happen, especially in the central United States. You have how full the plane is, which you can obtain. That says whether that will lead to give you information on whether it's likely to leave on time, because full airplanes generally don't get away from the gate on time. Then you've got the issue that the crew may be getting tired. This has happened to me a couple of times where you're on a flight, it gets slightly delayed, it gets delayed a bit more, then they announce they can no longer continue because they have now reached their duty limit. Which means for me to accurately predict whether my flight is going to be late, I now need to know when the crew showed up. Where did this piece of information come from? Then there's which part of France is shut today, which seems to be an ongoing problem. And I love this one. It's in Comic Sans for a reason, the most ridiculous excuse ever, the late arrival of the incoming aircraft. But all of these things are happening in real time. For me to join all these data sources in real time is a significant technical challenge because there's all sorts of ways they can go wrong. None of them will be perfectly in sync temporally. Everything's going to have a lag. Everything's lag is going to be different. Some of them may stop and start for no reason. Some of them may send you stop totally and not restart. So as volumes increase, imagine you're doing valet parking. Well, that's a fairly simple task. You know, any of us could set up a valet parking company. You just basically stand there, collect keys, and make sure you give them back to the right people. Unless it's Bournemouth Airport where you go bust and just don't come back. That was in the papers recently. Suppose my job is to do valet parking for oil tankers. As scale increases, the simplicity some business models don't scale evenly or well. If you're dealing with very large objects where you need helicopters and boats to get people on board and it takes 2 hours to get it started, it's not the same. The next point I'd make, and people tend to ignore this is relevant to machine learning, but it's also relevant. Once you're in this situation of having huge amounts of data showing up from multiple different data streams, it's not a one-off exercise. A lot of people would look at this and say, well, we just merge these data streams. So we do it once, there we are. When you go live, you're now in the business of doing this every day. You're now in the business of dealing with different groups of people. So just say we're really trendy and we do a machine learning application. We now need some data scientists behind it. And we need some developers. And now we need operations people to run all this. And if we're dealing with billions of records a day and 20 or 30 servers, this isn't going to be trivial anymore. People will go on holiday, people go on maternity leave, God only knows what happens. And then you end up with a HR and management involvement simply because you've got that many people. I love HR. And the last point I'm going to make here is what happens if time is of the essence. All of this thing has revolved around the assumption that I can do this in a calm and dignified manner, and that I've got plenty of time. If the problem space I'm in is even things like selling surplus hotel rooms or flights, that's time sensitive. If you're late with stuff, you're no longer providing value. We're now going from opportunities which had time horizons of days down to time horizons of seconds. So being late is dead now. So traditionally, batch Hadoop, you could be 30 minutes to get an answer back, and people would expect that. The traditional web server brought that down to about 3 to 7 seconds by the time people get bored. Spark, Kafka gets it to you in about 1 to 2 seconds. OLTP gets you down to 5 to 50 milliseconds. And the 5G phone network, or Volt, which we would respond in around a millisecond, maybe a bit more. I would probably not promise that, but usually. And the 5G phone standard is expecting everything to start responding in a millisecond, which is bonkers, but there you go. And the question is, what happens when you start doing this? As a real-world example of something we've done, is combines machine learning in an actual real-world use case that is time-sensitive and has high volumes. In China, when you use your certain credit cards, the bank now has an elaborate Hadoop data lake that describes China for credit card purposes. It describes the customers, it describes the retail outlets, it describes patterns of crime. It has all this stuff built into it. And they use it to generate rules in Java, which are loaded into Volt as stored procedures. And we execute, a couple of hundred rules per transaction? And we come up with a score saying whether this transaction is suspicious or not. Traditionally, credit card fraud works. You do something bad, and 25 minutes the bank later, bank rings you up and says, what did you just do? These guys will prevent the transaction from happening in the first place because collectively your score goes over a certain threshold. And so it's a real-world example of how the slide looks simple, but it's not. There's hundreds of stored procedures involved. There's lots of stuff being generated. There's buildings full of people working at this all the time. And with that, I'm done.